So now we'll switch to our panel, and I want to welcome also Shwetak up here as a third member of our panel. Shwetak is a professor in computer science and engineering here at UW, and also holds a position at Google. He's head of health. I forget your exact position now because I know you're involved in the home devices as well. But Shwetak brings not only a wealth of experience designing sensing and machine learning systems across a variety of domains, but also a lot of experience from industry commercializing those things and implementing them. So,
thank you.
Yeah. So then maybe did anyone have questions for the panel? Otherwise, I can get us started. Okay, yeah. So as a start here, I think maybe for Shwetak and Chris, I'm curious there are many applications where you have limited ability to place sensors. So maybe the two of you could share an example of this, and then Nathan, it'd be great to get your perspective on these models that you're developing that can actually operate on limited data. What are some opportunities that we might be able to use those methods to address this?
I can kick it off if that's okay. So one thing that Nathan's talk was really amazing because it was my remarks were actually going to be very similar, because one of the challenges that we see, especially for sensors that are constrained by power, and if you're deploying these things either on elephants or out in the environment, you've got to look at power constraints and those kinds of things. But these compressive training approaches and compressive sensing approaches provides this new ability that we just didn't have before, right? So if you have a link budget, so like if you're uploading at maybe a few bits per second, you've got a power budget. Some of the methods that Nathan showed, where you can actually, it's basically the bow tie, right? You've got the encoder, decoder, and you've got the pipe in the middle. These techniques can actually now allow us to do things that we just weren't possible before. So if you had something as simple as an accelerometer on an elephant, you'd had to downsample, and when you get to the end, it's like, okay, I've got a few pieces of motion information every hour, every minute. You just can't do much with it, right? But now if you can reconstruct the original waveform because you're able to encode and decode in a clever way, I think that's pretty interesting. And so I think my advice to everyone, and something that I think is really interesting, is maybe we can revisit some of these simple sensors and applying these kind of encoding architectures to things that we thought weren't possible before could actually be pretty interesting. So I think that's one area, is I think these techniques that Nathan showed, I think opens up some huge opportunity, particularly around reconstructing with low power and bandwidth constraint devices. The other one I think could be really interesting is like the multimodal aspect of these things. We often think about, we'll bring the camera data with the motion data and the audio data, bring it together, but we never end up doing that. That ends up becoming the future work of a paper, and we never do it. But I think this notion that if you take, again, Nathan's approach and kind of train it in a joint embedding space, you get this really interesting kind of combination where you kind of get it for free, right? Instead of trying to create this model later on where you bring together the audio, video, and motion. If you start to bring those data streams in together, that encoder will actually bring, like, the latent embedding will kind of bubble to the top, right? And so I think that's another area that I think you kind of get it for free if you use some of these architectures. So I think those are the two things I think could be really exciting in this space right now. And so anyway, those are the two things there. Yeah.
Yeah, especially for you talk about the accelerometer. I know these elephant collars, they transmit using satellites, so we don't have the bandwidth to send down that whole accelerometer data. So it'd be really interesting to see that being analyzed, and if we could send a smaller stream, because each elephant moves differently. So to know what slow is for one elephant, it'd be different for another one. All we can do at this point is just know the accelerometer has moved, so we know the elephant's moved. Yeah. But yeah, you could start studying. So they've also been down in South Africa, SP LaRue has been working on AI running on a collar for a rhino. And so it's a bracelet around their foot. And so using AI there to sense abnormal movements, or actually the rhino being pushed over, or other things. So yeah, that would be interesting. I think attachment's always been a problem. Rhinos, their neck does not allow you to put a collar around it, so they tried the horn, but then the horn would keep growing, and so then the sensor would become broken at that point, or they didn't waterproof it, and so and it's anyway, all these things. And elephants is so expensive, so you have to have a whole team go out with you to anesthetize the elephant. Make sure you have to have a vet to make sure he's stable. They put this collar on, so it's almost $10,000. So they've always talked about, well, could we just like tag it or put it on their tail? It's just nothing really works. So yeah, we're still trying to figure out the ultimate collar for an elephant.
Actually, just one kind of response to that. So, we tried this experiment where it wasn't done on an elephant, but we just took accelerometer data like from a wearable, and it's actually really interesting. So, trying this concept, we're able to kind of compress so you run a little model on the device, and it's like very small. It's like maybe 20,000 parameter model. So it can run on a little microcontroller, and then with just like maybe tens of bits per second of data. And when you reconstruct it at the end, using very similar approaches that Nathan showed, you can actually reconstruct the original waveform of the accelerometer data. But now you've taken this like huge bit rate requirement to like a few bits, and so you can actually stream some of this stuff to the satellite too. So some of these approaches you can start to actually see some of this in literature. So we've demonstrated it for wearable data. I think it could actually be pretty applicable for this kind of use case too. Yeah.
I'll definitely talk to some people about that.
Great. Maybe another question now for Nathan. So you mentioned that you're able to do these reconstructions of pretty complex signals, but there are of course going to be cases there where it doesn't match the either the full model or actual observations. So how do we think about how we should use these models that you're working on?
Yeah. So. In these scenarios, I think we're going to train on a data set, let's say. But I think actually, in many ways, the weather people have figured this out, the data simulation, where you're going to start saying, look, my model and my data are there. And when they agree, it's fantastic. And when they start to diverge, right, then you've got to figure out how to update your model to sort of get towards the reality. I mean, look, computer sciences call this the sim to real gap, right? And then data forecast or weather forecasting might call this data simulation. I think that's a fantastic area of where I think we're going to go as a field. We're going to have these really great models we train. We're going to figure out architectures to do it, compress, and then we're going to go out and deploy in real life. And it's like, okay, it works a lot of the time, and once in a while, it's just like my model and that data are completely different. How do I start to then update my model to actually match the reality in some kind of data simulation way? And I think there are definitely architectures out there. I'm a big proponent of using everything we did before. So all the governing equations we had, normal forward simulations, we built entire architectures and worlds. I mean, this thing is here that we're glued to, right? This is all from forward modeling, right? E&M, quantum mechanics, we extrapolate our way to this. And I think that we should retain all that knowledge, but now bring it into a much better framing with the data and machine learning aspect of it too. I think they're very valuable components. They can play together very nicely. In my view, that's the future of science and engineering and machine learning is you have people who are going to have skill set in forward modeling computing, in machine learning computing, and it's going to be this, I think, a very nice framework for all of it to live.
Thank you. So my question is for Nathan. So what if you can't get sensors that are durable enough to live through an event like ground surface of a tornado? How do you deal with that?
I don't know. Well, it's actually interesting. So in the framing here, you can really go to a very minimal number of sensors, at least in the data sets we've looked at. Whatever the dimension of your system is, D, you need D+1 sensors. Very much like you need 3 cell phone towers to localize you in a 2D plane, essentially. And so you could imagine, well, if I can do 3, I'll just throw 10 out there, and I'll train a bunch of these models with 3. They're super easy to train. And so then you can build an ensemble of these models, and you can also monitor, like one of them goes out. It's like, okay, the model's involved, involving that one, I'll throw them out, but I still have recovery with the others. So as long as they don't all go down, you should be in pretty good shape. That's exactly how to train it.
Yeah, and another kind of approach to that, Dorothy, is that with some of these new transformer architectures, what we found, at least in some of the data sets that we've looked at, which are all time series data, like accelerometer, like heart rate, and could be motion data from GPS, is that you can do what's called data imputation. So here, if you only had one sensor, and if the data went out for some reason, the battery went out, the device fell off the elephant or whatever, you can actually impute, interpolate, but impute in a very smart way, where because if you have enough of the time series represented, you may be able to reconstruct the intermediate waveform to a point where it's still useful enough, right? I mean, you can't impute the whole day or maybe a week, but if there's like dropouts, there's some of these new techniques have actually shown that they're pretty good at kind of forecasting what it would have looked like in the middle. And you can actually experiment with this in your data set. So if you have your own data and you can do this retrospectively, where you take the big matrix of data, pull pieces off of it, and you train that model with different data sets the different time series moved out or removed out, and you can actually create an imputation model, which can actually be pretty resilient to some of these dropouts. So yeah, it'd be interesting to take a look at that. Yeah.
Great. Do we have, maybe I'll check again, any other audience questions? Yeah, here we go.
I have a question to Nathan. So if I have a space-time model of some three-dimensional evolving, and I have a complicated model, it takes a lot of time, and I want your model to be trained on that. And in my computation, I can give you thousands of sensor points. So how many sensor points is good for you? If I have all the points, then is that, is that a problem, or do you need to really sparse points? And the second related question is that in models we have discretization of the surface, like the grid cells. Do you have, like, in the sensors, you're sampling from a point. Do you have any sort of thoughts about sort of putting the right scale when you're simulating a three-dimensional domain in terms of grid space with those sensors?
Good question. So let's start with the second one first. In terms of where you place them, part of this is depending a little bit on sort of a global structure that you have of dynamics happening together. So obviously if you have local physics that's separate from other local physics here, you definitely need a measurement in each location. So any statistically independent region, you better drop a sensor in that place. Now, as far as the number of sensors, so this is interesting because nobody quite believed this initially. So the reason I knew this was an amazing technique, so one of the coolest things I did last year is I worked at McLaren Formula One racing. They're leading the championship right now, which FYI. They're awesome. Anyway, that was a really fun year. But one of the things I told them, I said, look, I could take your pressure taps all over the car, and you have your flow physics in the back with PIV. And I told them you could just pick any three and do that. They wouldn't believe me. Like, come on, we got a bunch. Let's just do better. So I had to do the experiment. It's like, okay, I'm going to randomly pick three and just train it a bunch of times. I'm going to give you 4, 5, 6, and you just show it. You get to 3. There's essentially no improvement with more. I could do it with 3. I showed him, and he said, yeah, but it must be the right 3. It's like, pick any 3 you want. How many do you want me to run? I'll run it 1,000 times for you with 3 different, 3 choose 200. And it's so counterintuitive to them, right? They would not believe it until I did the extensive experiment. But by doing that extensive, because again, nobody quite believes this mathematically sound idea of Tauquin's embedding theorem. It's sitting there black and white. It's 50 years old. It's a mathematical theorem about dynamical systems. And it's so counterintuitive to, you just don't believe it. Clearly, I would do better if I had 100 sensors instead of 3. It's like, yeah, well, guess what? No. The answer is no. And in fact, this is kind of interesting. I think you actually do better with less sensors. You overtrain on the 100. You get the overfit on that. Whereas the 3, your ability to do things, actually, your ability to generalize or extrapolate seems to be a little bit better. I can't prove any of this stuff, at least. This stuff I'm just making up, just observations. But with the 100, you're just overfitting because it only needs 3, and it says, okay, but I got 97 others that have to contribute to my model, right? So it's forcing it to say, okay, you have an opinion, and you have an opinion. Like, let's all... It's a little bit sometimes when you make group decisions, right? It's actually sometimes not as good a decision because you're accommodating everybody's thing versus sometimes you just need somebody to say, here's what we're going to do, go. All right, sorry, I didn't mean to bring political dynamics into this, but there we go.
Taking the system 3D. This is the example I'm thinking.
Yeah, then you would sample with 4 points. And then, but if you go 3D volume, we've done 3D volumes. If you sample 4 points, you're fine. Works just as well.
So that would work.
But we typically just would compress the data. So we just do compressive training. So you take the data, flatten it, boom. Just do it all in that. Works really well.
So Nathan, I have another question. So if you do the forecast aspect of it, do you just do the forecast in the reduced space, and then you do the decoder? So that would make it really cheap, right?
Yeah, exactly. So what Mars worked on out there was if you write down now, if you basically, part of your loss function is to develop a dynamical system in that space, then that's trivial. In fact, if you say, I also want a linear model in that space, I don't want just a nonlinear dynamics, I want to lift it to a higher space. So Mars was able to show in the video of the fluid flow, oh, here's a 6x6 linear ODE. Well, you can just write down the solution to it. So when we forecast, the forecast is like trivially inexpensive. Because you say, I want to forecast it way out into the future. You say, I have the exact solution. You want it at time 1,000 years? Put t equals 1,000 years. Throw it back through the decoder. Yep, that's right. When do you want to look at it? It's a little bit like our phone concept, right? I mean, the whole world works on compression, decompression, right? Your pictures aren't big in here. They're compressed, right? The only time they are big is when you say, can I look at this specific picture? And then it decompresses to show you. Yeah, it's the same concept. So you live completely in the latent space. And I think that's kind of a concept where everybody's moving to. Successful strategies are all about do everything in the latent space, give your machine learning freedom to build the latent space it likes, right? Pretty much that's, like, we could totally high five on that one, because that's the architecture.
Yeah, well, I guess one quick comment. I know you have a question, but kind of something that's implicit, but maybe it's worth talking about is that, a lot of us, or at least a lot of you, a lot of us see large language models have these scaling laws, right? You throw more data and features at it, and you increase the dimensionality, it just gets better and better. But in the sensor space, it's actually different. The scaling laws are actually really different. And so, to your point that a smaller number of sensors could actually go a pretty long way, in fact, could be better than more sensors, is very counter to what we're seeing in text and language. And so that's something that's good to recognize, and I think there's this implicit bias to let's just throw more sensors at the problem because it's solving, LLMs are actually benefiting from it, but not every sensing system actually benefits from that. So I think that's something to just actually recognize.
So I have a quick question about the Earth Ranger. So usually, how big is the data of the positions and accelerometer? And then also, my second question is, do you collect any other data than the positions and the acceleration of the animals?
So the size of the data, I mean, it's the lat for coming off the elephants. It's just a lat long, and then the recorded at, and then usually these collars have like temperature probes on them, and then the battery level. That's kind of what we're capturing from there. So it does compress down pretty small. It's just as numbers. Let's see, what was it? And then what was the second part?
How big is the data?
Yeah, I mean it's pretty small. It's probably just like 10 bytes or something like that at that point.
That makes sense. Thank you.
Yep.
Maybe one last quick question to each of the panelists to round out the session. With the methods or areas that you're working in, what is maybe the one of the most exciting things that you think AI can do, either for conservation or other environmental challenges? Maybe to each of you. Yeah.
Yeah, I'll start. So exciting thing would be this movement ecology. So starting to run we have enough elephant data now to run models to see behavior of elephants so that we can better predict when human-wildlife conflict could occur. And that it's also bringing in, satellite imagery sensing data to help build out that model, that whole picture. Is it weather? Is it, crops are coming in, other pieces that we don't really quite fathom. It's more difficult across Africa just because there's less want for satellite imaging. So if you need satellite imaging over the U.S., no problem. They're doing a ton of that. It's hardly any in Africa. No one's paying for it. So it's been hard to really get sensors out, and the areas are so vast, but no one's putting money into it. So that's the hard part, getting good data to train on. So that's what's exciting. We're finally going to start getting there as far as having enough data to do that.
Yeah, for me, I'm going to pick two. One is I'm just going to plus 100 the use of encoders for compression for sensors. But the other thing that I think is really interesting is that in a lot of our domains, we have a lot of data, but it's unlabeled, and so labeling is really hard. But some of these new architectures are really fascinating, where you can have a giant data set that's totally unlabeled, and some of these models are able to get at least glean some structure out of the data. It's unlabeled, but you can get some structure. And then you have this little tiny data set, which is highly labeled, which is attainable. And then when you bring those worlds together, the ability to actually create these models that can actually be performant on this other data set is actually becoming a reality. Like, we're seeing this in other domains. So I think that's the thing that's very exciting right now, where these architectures that need very small amounts of labeled data that benefit from a whole bunch of unstructured, unlabeled data, I think is really exciting. So I think bringing that into this domain, I think is going to be really exciting, because we just can't label everything. So that's one that's really exciting for me.
All right, so for me, the thing I'm super excited about, I want to make a historical remark, which is it took us a millennia and a half to make a coordinate transformation from the geocentric to the heliocentric, and that revolutionized things, that brought in calculus, brings in a whole new framework for doing science. 1,500 years, right, just to do something so simple. And I always think about physics as a way to, what you've got to do physics successfully, you need the right coordinate system to write the model in. And I think of the future as GoPro physics, which is, I'm going to go film this, and this thing understands that it has to find a coordinate and a dynamics jointly. And that's all going to happen in the latent space. I'm not going to, so for me, I'm excited about the prospect of scientific acceleration for us to discover things much more rapidly. Not that we couldn't do it, but maybe, hey, I spent the last 10, 15 years of my career looking at this problem to find out that I should use this variable. Because that's kind of what we do. And that's a big step for us. But I think we have an architecture now, like, I spent an afternoon and I found this variable, okay? The hard part about that is you'll have to now interpret that, whereas when you've had 15 years to digest it, by the time you find it, you kind of like, oh, I know what this really is. You're going to find it in an afternoon and go like, okay, now what, right? But I think it's exciting too, right? It's going to give us lots of options.
All right, great. Let's thank our panelists one more time. And also thanks to all of you for coming. This concludes like our main session. We still have this space until I think around 6 o'clock. We've got some snacks outside, the posters. So please use this chance to connect with others that are here. And thank you so much for coming again.